Okay, this is an example of a sinusoid force, which is non-constant, which means the acceleration is not constant, and that in turn implies we cannot use the constant acceleration kinematic equations. This is a calculus problem. Imagine we had a particle whose initial velocity was 0 that was acted on by c sine pi little t over big T. And so I plotted that over here. This is going to be the first half cycle of a sine wave when little t is equal to big T, sine of pi is 0. And so it's going to start at 0. At t over 2, it's going to go up to its maximum of c, and then it's going to go back down again. This has the shape of a sine curve. Um, Please notice that c has to have the units of newtons for this to be a dimensionally consistent equation. So we're asked to find what the x velocity is over the same time period that this force is applied. Um, T, in other words, varying from 0 to big T. So here's the free body diagram. The two vertical forces are going to remain constant as a function of time and do not enter into the problem. The x force is going to vary in magnitude. The direction is always going to be rightward. It's going to start, well, essentially you can see what's going to happen here. It's going to start at 0, go up to a maximum of c, and then go to 0. So I've chosen some arbitrary time in between 0 and big T. And so if we write the x component for Newton number 2 for this, here is the sinusoidal force. That's the only x direction force. That's going to be the mass times the acceleration, which is m times dv dt. Now I can multiply both sides by t. In the parlance of differential equations, this is separable, so I can get dv on one side and dt on the other. And if I do that, on the left I have the integral of dv from 0 to v, and on the right I have the integral of a sinusoid times an amplitude from 0 to t. And so v is that integral which entails integrating a sine. Integrating a sine is going to give a negative cosine, and because of the chain rule, we have to multiply by t over pi. And so minus t over pi cosine pi little t over big T is the integral of this, the indefinite integral of this, and we're integrating that from 0 to t. So the cosine of 0 is going to be 1. That's what generates this 1, and then minus the other limit is cosine pi t over big T. So that's the expression for the velocity as a function of time. And so you can see, if you look at this, that if at v at 0 is indeed equal to 0. If I put little t equal to 0 in the second term, I get 1 minus 1. And if I put v equals big T, I'm going to get the maximum velocity. If v is equal to big T, then cosine is pi, and I get 1 minus minus 1, which is 2. And therefore you have the plot of the velocity as a function of time, which goes from 0 to big T. It's going to be in the shape of a cosine, and it's going to max out at 2ct over m pi. That's going to be the maximum. So we should definitely check the units here. The of ct over pi, 2 and pi do not have units, but ct and pi do. So the units of ct and m had better be velocity to be consistent with how we're interpreting this. So the units for c are newtons. From the first equation, we argued that had to be the case. This has to be in newtons. So there's newtons. Big T, of course, is seconds, and m is kilograms. And so newtons is meters times seconds to the minus 2, but divided by kilogram meters to the second minus 2 is newtons, but this kilogram cancels that out, and so what's left in the numerator is meters second to the minus 2 times seconds, which is meters seconds to the minus 1, which indeed is speed or velocity. And what is the maximum velocity? Well, we've already weighed in on that. It's 2ct over m pi. That comes out of the integration that we did here, and realizing that this is going to be 2 to make that a maximum.